I'm going to continue from where we left off last time. So last time, the last thing we talked about was the attention is all you need paper. So the paper that popularized the transformer architecture. And GPT-1, 2, and 3, all of them are using this transformer as like a building block. So in GPT-1, the main points, like main distinguishing features from the previous literature, is that it uses transformers extensively and like pushes the limit up to like whatever was done until that point of time. So they are showing that transformer works significantly better than LSTMs or by LSTMs or anything like that. Then they are showing the effectiveness of language model pre-training. So the reason this is very important is because in computer vision, people say that one of the biggest contributing factors for industrial adaptation was fine-tune pre-training on like a large data set and then fine-tuning on your custom data set or your custom task. So in the pre-training phase, your model usually learns some useful features, and then those features are used in turn on the task that you are fine-tuning on. So that opened up a huge array of applications, because for every task you don't really have a huge data set. So it allowed this pre-training. It showed that you can also do the same thing in pre-training on a larger scale. So there were a few papers which had similar ideas, but this pushed the horizon a bit. The other thing is that, okay, once you do pre-training, you do fine-tuning on specific tasks, and they show that a combination of these two is significantly more effective. And the other thing is that we talked about what are language models, how, like, so they are a black box, you generate language from that. But GPT paper, they showed how you can use just a language model, a barebone language model, to do certain specific tasks. For example, question answering or sentiment classification or sentence similarity or something like that. So those things, they need some kind of tweaks in the inputs to make them work. So those are like the main contributions. The reason I'm spending more time on this is because this is the same thing that gets exploited in GPT-2 and GPT-3, just at a significantly larger scale. By the way, if you are messaging, just say it out loud if there is a question. That's much easier.
Oh, okay. I wasn't sure if this is the right time. So I had a couple of questions based on your previous presentation about transformers. So one was, although you said it's quite complex, like if you could maybe tell us a little bit about what these keys, values, and queries are. Because I mean, I was wondering if they correspond to inputs, outputs, and embeddings, but I'm guessing they don't. And the second question was, I saw later, I was reading and I saw that there's something called a residual connection also in transformers.
Yes.
And what does that?
Okay, so actually we are going to go through a little bit of that, and I'll go back to keys and queries and stuff. So GPT architecture is in a way very simple if you take transformer as a black box. So this entire blue, where is the cursor? Okay, yeah. So this entire blue thing is this transformer. They stack 12 of them together, and then they just add a fully connected layer to project it on your probability output. So let's say your number of the vocabulary says 50,000. So then they add whatever is the dimension of this cross 50,000 fully connected layer, and that becomes your architecture. So it's significantly simple if you assume that transformer is something that is given to you. So that is there. Now, this is what we talked about. So let's talk about residual layer first. What happens sometimes? So the reason residual layer is used is that whenever you do any computation in a neural network, you, in the back propagation, you compute the derivative of that computation. So each box, whatever computation that box does, the derivative of that computation is back propagated, and the weights of the previous boxes are adjusted with respect to that. So that input of the next layer's gradient is used here. Sometimes what happens is that in this process, and like the chain rule of calculus, you have the derivatives are multiplied if it's a composite function. So sometimes what happens is that because there are 12 of these stacked together, when you go towards the beginning of the network, the gradient information is diminished significantly, and then the initial layers are not learning a lot. So in computer vision, there was the ResNet architecture. They said that, oh, if you allow this connection, what this means is that whatever is the input here, you process the input via whatever function happens here, and then you add that input just as it is. So let's say this is x, this is fx, so this thing becomes fx plus x. The reason this helps is because now the gradient not only goes via this thing, but the gradient of this layer also goes without any change via this blue connection, so that it does not get diminished when it goes towards the beginning of the network. So this is just a very clever trick to make the network learn well. So ResNet was the initial motivation, but then there is this field of neural architecture search where they just create a network to build a neural network. Now neural architecture search usually comes up with this residual layer. It seems that this residual layer is an important thing to make the networks learn well. So that's the only contribution of that. Does that make sense?
Yeah. So you're saying this is this is the same thing as vanishing gradient?
To to prevent vanishing
To
gradient.
prevent vanishing gradient.
Yes.
Okay. So LSTMs help prevent that because of their the hidden state and the self state, right?
So that is also slightly similar. So in LSTM, that other gate which allows you to forget or remember something, via that gate you are deciding, do I need to propagate this information as it is, or do I need
Huh.
to do anything to that? So you're basically allowing propagation of information without any computation. So this is also very similar. So its
Okay.
idea is very similar, just it's a different reincarnation. There are no gates or anything here which you need to learn. It's like a completely simple addition that you do to the input. That's it.
Okay. Okay. Cool. Thanks.
Yeah. So this is the transformer block, and the key point of transformer is whatever happens here, the shape of the input and output remains the same. That's the key point. It's transforming the input into something. That something is a function of all the inputs combined. So that was the key point that we made last time. So that's a transformer. The other thing we talked about is masking part, which uh, allows which prevents the GPT from cheating. So whenever you are predicting the first input, you don't look ahead. That's something we talked about. And the other thing is this positional encoding. So because we lose this information of which token or which word is in what location, along with the embedding for that word, you also pass the embedding of the position. So there are two ways. Sometimes you just pass a random one, and you also allow the network to learn that position encoding. But GPT said that even if they, so this is what this is that every row here is a sinusoid of different frequency. So this is the small one, then this is slightly bigger one, this is slightly bigger one. So zero position has this encoding, the one first position has this encoding. So whenever you pass the embedding of the token, you just add to it the embedding of this thing. It is just in order to distinguish the first token from the second token to the last token. That's the whole purpose of this thing. And this is this is another clever trick that people use. And every time in all these large models, there are a ton of these tricks being used. So yeah, these
Here,
are the three things that we. Yeah, go ahead.
Here, D is the dimension of the embedding model, and L is the length of the sequence input, right?
Yes. Yeah. So D is the dimension of the embedding that you need. Because you need this to be the same size as the embedding for the word that you generate, right? Okay. So
Yep, got it. Thanks.
okay. So do we want to go through the key value thing just once, so that okay, let's just do that
Thanks.
once. Let's do that once so that everything is clear. So the idea of key value is that the whole purpose was that whenever we are processing, whenever you are generating even one token, or whenever you are processing one of the input tokens, we need to get some information from the other tokens in the input, right? So while we are processing, let's say this one to generate this thing, we need to look at all the other tokens that we have already seen, or we are going to see. So in masking, you don't see this one, but you see the other one. So we need some kind of information information propagation from the existing from the other tokens to the current token. That is the basic idea. Now the way this is implemented is that in the completely basic case, what we can do is we can just create separate weights. So the weights are let me see. Yeah. So the weights are the some random numbers which are multiplied by the input. So whenever, let's say, while processing this second last token, I need to get some input from the first token. So I multiply by a corresponding weight for the first token, and then do the same thing for second, third, fourth, and add it together, and that becomes my output. That is like the simplest way possible, but there is no learning happening here, right? So what we are going to do, so here, and the weights, we don't know what the weights are. So in simplest case, weights are going to be the dot product between the token that we are processing and the token that we are paying attention to. That is the bare minimum way of doing attention. You are just allowing a dot product to give some importance to the embedding of this this token. That is basic. Now you want to be able to learn that. So in order to learn that, we introduce three matrices: the query matrix, key matrix, and value matrix. So the name here is not important. The only thing is that query is something that you are processing. So while you are processing I, you are computing this key and value for every other token in the sequence, and then you are computing these weights from that. That's the only idea. The query, the terminology is a little confusing, but if you think about the previous example, we are just allowing the current token some inputs from previous token, and the weights of those inputs are governed by these query, this key and value matrices. That's the whole idea. If you implement that, so I haven't implemented, I'm going to put that implementation to the same repository as I created for the other thing, and that will make it slightly more clearer. But for now, you can just think of transform as like this black box which creates same sized output as the input, but this is some kind of entanglement between all these input embeddings. That's the essence. Now, the special thing about GPT is that we are doing this unsupervised pre-training. So similar to what we saw in the previous talk, where we were training an LSTM or a fully connected layer on just predicting the next word that is going to come in the sequence, right? Similarly, here input is a sequence. That's it. So this is the basic barebone language model where you get a sequence and you want to predict the next token. The architecture is very straightforward. You get the embedding matrix, you get the position embedding, you add them up. Then you have like your 12 transformers, pass all of them through transformers, and then apply this softmax layer of the size that you want, and that becomes your output probability. So that's like the very straightforward architecture. And the objective function, exactly what we saw. We want to maximize the probability of the actual token that is going to come after it, and minimize the probability of others, so that we are just increasing the softmax score for that token. That's it. This only consists of the pre-training part. So just doing that will give us a good language model. That is only one part of GPT. The second part is the supervised fine-tuning. So unlike GPT-2 and GPT-3, this is not like a prompt-based thing, like prompt-based language model that you play around with and get answers. This is supposed to be used for a specific task. So let's say question answering or sentence similarity or something. So in that case, once you are done with the pre-training that we saw before, you have this another phase of fine tuning. This is very similar to what the things we do in let's say image classification or something, where you have your once you do some kind of pre-training, then you have your own data set and you do fine tuning of that. So this data set is different, where you have a sequence of tokens, and then there is the answer token, the output token. So this could be yes or no. For example, sentence similarity, it can be some kind of score, or is it similar or is it not similar, or it could be entailment, meaning so you can encode two sentences here with some kind of separator, and this will say, does the second sentence follow the first sentence or no? So yes, no, it can be answer prediction or some kind. It can be anything. So you the input is different from what it was before. So the y is not a sequence after xn semantically, but I mean, we are going to train the model in such a way that it predicts y as a sequence. So output probabilities are also similar. Instead of so now we have, like we saw in the architecture, we have this after the output layer of the final transformer, we can pass it to another fully connected layer to predict the probabilities of specific class. So you multiply by a fully connected layer to get the probabilities for your output tokens, and this becomes our objective function. It's very similar to the previous one where you want to maximize the probability of the answer token. Now, the other thing that we observe is that while you are fine tuning on a specific task, it helps if you add the language modeling, the language modeling objective function along with the task objective function. So the language modeling objective function was this: while if you have seen part of the input, then we want to maximize the output of the next token. So while doing this, we are also accumulating the loss for this one. So while we are inputting a question, the model is also trying to predict the question in a way, and then it's trying to predict the answer. So this becomes the entire loss function. And they have some results where they show that adding this does help significantly. And they have this something called ablation studies where they remove one part of it and they compare the performance. So this is the entire essence of GPT. GPT-1. So now, how do they transform the inputs to perform these specific tasks? So we want to do classification. Now what they do is that they have a start, and this extract is, I think, end token, but the paper, they don't specify this. Most likely this is the end token. So they have a specific start token and an end token with its own embedding. And then this is all the entire text embedding. That becomes the input. It's passed to a transformer, and then there's a linear layer, and that will say yes or no or whatever is the classification output. So that can be like 2 or 3 or 4 or whatever number. You can decide that number, and that becomes the output. And then you train it via the objective function we saw in the previous slide. Similarly, entailment is like whether this hypothesis follows the premise or not. Similarity, because there is no order in the similarity task, so text 1 can be similar to 2 or 2 can be similar to 1. They pass both of them, and then the addition of the final transformer layers for both of them is passed to the linear layer to predict whether it is similar or not. So yes, no is the answer here. Similarly, there is multiple choice question. So they change the input to do a specific task via language modeling. So this is like another engineering like hack they do in order to make language model work on your task. So the important thing that they showed in this paper is that transformers are significantly better than LSTM. So here, if you look at, so by the way, these are all different tasks. This is, I think, linguistic. I forget what, I think it's question answering. I forget what are these tasks, but these are like different tasks. This is does the language make sense or not? These are, so whenever you see accuracy, it's trying to predict a token. Whenever you see PPL, it's perplexity. PPT is perplexity. F1 is F1 score. So every, like, it's just a number higher the better. That's it. So it shows that LSTM with that auxiliary language modeling laws performs significantly worse than transformer with transformer without the auxiliary laws. And once they add the transformer with auxiliary laws, in some of the cases it works better, in some of the cases it works so, like not too bad, but yeah. So there are cases where it helps, it doesn't help. Then it shows that you when you do the pre-training, it almost always helps. So without pre-training and versus pre-training, there is like significant difference in the first two lines. So that these are the key takeaways. Like so, I mean, these are clearly nitpicking. But if you look at the numbers, it's changing the game. So now people know that you should always do that if you are using a model which is a language model to do your task. You should always use auxiliary laws, and you should use transformer instead of LSTM in most cases. There are still some cases where LSTM work better. There are a few paper after that, but anyway, so this is the key takeaway of GPT.
I have
Uh,
a preliminary question. How do language models get used for sentiment analysis? So I think the search bit makes sense to me, question answer makes sense to me, but how do you use it for sentiment analysis?
So sentiment analysis is also like multi-class classification, right? So sentiment can be positive, negative, neutral, and then you just ask it to categorize it in any one of them.
But where is it learning whether how does it ascribe that value to the different, I don't know.
So what happens is that because we know that, okay, now we decided the sentiment analysis is multiple choice question kind of thing. So you want to decide whether it's neutral, this or that. So then you so this becomes your format of your input. And then there is a fully connected layer. That layer only outputs 3 probabilities. So that becomes the score.
I see. Okay.
So you have to generate, the problem is that you have to generate the data set here. So that is something that they address in GPT-2 and 3, where this is a big issue because every time there is a new task, people have to pay money or manually put in hours to generate these data sets. So the GPT-1, you have to do that.
Okay.
So now so this slide is very important. This is like continuation. This provides a continuation from GPT to GPT-2 and 3. So here this something, so they observed something in this model. So one thing that they observed is that, why does pre-training help? So that was like an honest research question. Why pre-training helps significantly in language? So they evaluated this by zero shot and few shot learning. So they said that because most of the tasks that we do in NLP, like question answering or sentiment analysis or whatever, all of them require some kind of linguistic capabilities in the model which are shared. So all of them require to understand, let's say, what is a noun, what is a verb, which is connected to which, all these kinds of things. So they said if the pre-trained model itself is learning something like that, then there might be a way to see that. So then they come up with this a few tasks which they call zero shot and few shot. Now this is different from if you have read anywhere about zero shot or few shot learning in computer vision. This is very different. This does not involve any back propagation, so there is no learning happening here. You have a completely trained model, and then you pose a problem like this. So for example, in zero shot, one example can be La Révolution Française in English. So that is the question, quote unquote, the prompt, and then the French Revolution would be the answer. That is zero shot because you're not giving any example. It's just the description of the task. The few shot or one shot could be where you give some examples. So Microsoft, Bill Gates, Apple, Steve Jobs, Amazon. So it would recognize that these are one of the famous founders of these companies. So Amazon, it would say Jeff Bezos, right? So this becomes few shot. Both of them, you are not doing any back propagation. And they showed that for the few shot learning and for zero shot learning, the performance significantly improves as you keep training the model. So in the process of training the model, the performance keeps improving. So just the fact that it's learning some linguistic statistics or some structures, that allows it to solve certain tasks. So that is one of the main takeaways from this paper, which allows them to experiment with GPT-2 and GPT-3. So this is the entire idea about GPT, where you have so the main goal was to enable unsupervised pre-training. Unsupervised is good because you don't need like a training data, you just need dump of text, and then you fine tune it on your task. But then it enabled this few shot and zero shot paradigm. It was already there, but it did not work this well at all before.
Swear, I had a question here. Can you just go back to that slide once? So when we are talking about few shot tasks, so the first two examples here, Microsoft and Apple, if you're saying that there's no back propagation, so for example, how are we passing these as, quote unquote short? So for example, are we just concatenating Microsoft and Bill
Yes.
Gates in our
Yes.
input sequence and just passing it to the output?
Yeah. So this is just like if you add quotes here and if you add quotes here, that is just one string.
Oh, got it. Understood.
As if it is
So it's
x1,
just
x2,
predicting,
x3. Yes. Next,
yeah.
whatever is the logical next token, it's going to predict that.
Understood. Makes sense. Thanks. And second thing I wanted to check, actually, it's a more general question. Is pre-training just, an implementation or of the concept of transfer learning in general?
Yes.
Okay, got it.
It is exactly that. So you pre-trained thing is a well pre-trained model is capable of transfer learning to a task. That is the gist of it.
Yeah, makes sense. Thanks.
So
So
Swear,
yeah, go ahead.
the previous slide. Yeah, so I just wanted to ask. So then, for zero-shot learning to work in this example, so all this Microsoft, Bill Gates, Apple, Steve Jobs would need to be there. Would need to be there when the model was trained, but not necessarily in this form.
So I actually skipped something which I should not have. So the examples that I showed, what I was doing was that I was going through all the words in the text and creating a vocabulary out of it, right? So
Yeah,
for example,
okay.
when I trained on Shakespeare corpus, I was just taking each word and that became my token, right? Now one problem there is that Microsoft is never going to be in that token, in that token list. So I mean, if you train on web text or like common crawl or something, then obviously it will be there. But it's possible that some weird word may not be there. So the way they create tokens is different. So they train a tokenizer. Train as in they basically pass. They have a layer of tokenizer where they don't keep, for example, Microsoft as a token necessarily. It is possible that Microsoft consists of micro and soft, and micro occurs significantly more time than Microsoft. Then micro and soft can be broken into two tokens like micro and soft. And so when you pass this as input, this first gets tokenized. So if Microsoft is not a word, then micro and soft can be a word. Even then, I mean, so it loses the meaning for us if you have separate words like that. But for the language model, just a concatenation of tokens. So the way GPT and BERT and all these new models are designed is that it works on these learned. These are called byte pair encodings. So they learn a tokenizer separately, and their model is trained on that tokenizer. So whatever be your input, it will find some way of representing that input in its own vocabulary. So in worst case, they also have individual alphabets as part of the vocabulary. So in worst case, Microsoft can be represented as M, then I, then C, then R, then O, then S, O, then F, FT. So it's they find a way to represent that, even if that is not part of the vocabulary.
But to Kritika's question, it then will not be able to draw the connection between Microsoft and Bill Gates.
It will, because while training, whenever it saw Microsoft, then also it represented Microsoft as the same sequence.
But Microsoft and Bill Gates have to be there somewhere in the initial training data, even if they are not together as company, founder format, right?
Yeah. So usually that is the case. So you most likely find these. So all these proper nouns, they are there. Otherwise, whatever it will do won't make any sense. So the fact that this makes sense, it means that it did see Microsoft in the form that it appears.
Right.
But my point is that it is possible that even though Microsoft appeared in the training data, Microsoft as a token may not exist in the vocabulary. So vocabulary might still consider Microsoft as micro and soft.
Sure, but I mean that makes sense. But also that's to say that if it did not exist in the training data, right? It can still represent a new word. That makes sense, but it cannot draw connections between that word and like some of the other things in the training data, right? Like for those
proper nouns, it cannot. But for let's say you have ing and you have some new word. So that word and ing has some connection to like a continuation of something or that word or something.
Right.
So for other things, you can generate things that partially make sense, but for proper nouns, you're right. It'll make some gibberish connections. It won't make sense. But for other things, it does make sense. So actually, you know what? In that spirit, let me just show you what kind of. So this is, I was just looking at the vocabulary that BERT generates. So whenever there is a hash, it is like a it has been cut off from a specific word. So rights, rights, then sling, then ghi. So it doesn't necessarily have to make sense, but something combined with ghi can make a word. So but it has learned some kind of embedding for ghi. So I mean, for us, there are so many. There are like 50,000 of these, 30,000 of these, and then you combine combination of these will give you. And some of them, sometimes you also have like, let's say, proper nouns here. So Dunkirk is there. So for those things you have tokens, but other things you can like separate them out. So that's how it usually works.
What's the difference between the hashes and the non-hashes?
So hashes are something that have been cut off from something that was before it.
I see.
So they go after. They don't usually stand. They don't start a sentence. They are like after a word usually.
Is there also a representation for a word and then a hash after that? So things that begin words, like anti.
So anti stands on its own, I think. Yeah. So then anti, and then you can have hash something. So that becomes a new word.
Non, I guess that's also a word in itself. Yeah. Okay.
Yeah, sure, for sure. Like everything like that would be a word. So anon will be. I'm pretty sure that it will be a word. Oh, apparently it's not. So you see different. So the fact that you see non-fiction and non-stop, it means that non is not a word, because otherwise it would have removed non and then created hash as stop here. So the way this is done, it basically counts the frequency. So the whatever data that I trained this thing on did not have significant amount of non XYZ. So it did not separate out non. Right. It's just frequency based. Okay, so, but yeah, that was actually a very useful question. I was debating should I put it or not, but it's good that it was resolved. Okay, so now we go to GPT-2, which is like a bridge between GPT and GPT-3. So now the main contribution I would say for GPT-2 is that they essentially decided to remove the fine tuning phase. So now it's all language model. And then they said, okay, we'll just go with significantly large model and a lot of data. So for that, so the data comes from not exactly Reddit, but they go to Reddit. Then they go to like very popular subreddits. They go to highly voted posts, and then in those posts there are links and stuff. So they crawl those links. So it has some approval from community or something like that. So it's not just random web pages, but it is some kind of ordering. So you get quote unquote important pages first, which are a dump bunch of text, and they do some kind of cleaning on that. So that is also a very time consuming and important part of it, but we just gloss over because there is nothing fancy going on there. Okay, so now from 110 million parameters, we are at 1.5 billion parameters. Unfortunately, why the time this was generated, there was a 17 billion, and then this looks all very insignificant compared to that, but this is like 10 times more. So it is significantly more. Okay, so GPT, now we are only talking about everything language modeling. There is no fine tuning. There is no specific. I mean, there is specific task, but it's not in the way that we change the input to fine tune the pre-trained language model on something. So one important takeaway from this paper is that when so this scale, this beginning is similar to GPT, and then this is 1.5 billion. So that is GPT-2 final biggest model. In this process, one extremely surprising thing for me was that the perplexity keeps going down. So not just on train, but also on test, perplexity, as we talked about, is like the higher the probability of generating a sentence in the test data set, that means the lower the perplexity. So the model is not quote unquote perplexed by seeing that sentence. So it somehow understands, quote unquote understands natural language. That's the notion of perplexity. So this kept going down, even though this is counterintuitive, because I usually when you increase parameters, the traditional machine learning wisdom says that if you increase parameters, then you are more likely to overfit. And then on test data set, at least you should see perplexity rising at some point of time, right? Because you're overfitting. So if you see something that you have not seen before, then you are likely to be surprised by that. So perplexity should rise, but it does not. So they try from 12 transformer layers, they go to 48 transformer layers, and then they also increase the dimension. So now we can have significantly more the size of the quote unquote context that we pass to the model. And they experiment on all of them to see what is the effect of increasing the size of the model. So here, okay, so by the way, this,
sorry, one small
yeah,
question. Why is this
sure.
scale from 2 to 16 perplexity?
Just like it's cut off. Also, it's log, it cannot be like 0 or something. So,
okay.
So there is no specific reason. It's just they show like that.
Okay.
I mean, so there are cases where on certain data set it does go down to here. So maybe they have the same scale for all perplexity, but no specific technical reason for that.
Okay, because I thought perplexity was like expressed as a percentage.
No, it's like 2 raised to minus log of the probability of seeing something like that. So it's not that, yeah. It's just a number. There is no this. I'll show you the formula, but it's not very important. So here now, okay. So there are two things. One, this is like pure language modeling performance. So the perplexity, right? Now we want to see language modeling ability in some context. So these are different tasks. So for example, this task is you are given like a very long sentence. So usually for this data set, I know this one, it is like a 50 word long sentence. And then you are tasked to predict the 51st word, something like that. So for that, they measure accuracy, and then in the process of generating, they also measure the perplexity for those. So for that, this was the state of the art for zero shot. So it's significant improvement. So perplexity, it's gone down from 99% to 8%, which is ridiculous. I mean, no one would have expected this kind of result. And also, like if you see from GPT to GPT-2, it's very big improvement. And this kind of pattern you see across different data sets. So for these data set, predicting the next word accuracy also improved drastically in some cases. And by the way, this is an outlier. The reason this is weird is because this specific task involves shuffled sentences. So there is no, it is entirely possible that from going from one word to the next word, there is no relationship. The task is just designed that way. So you are ideally you train on that data set, then you test on that data set to get a good answer. But this language model, because they are trying zero shot, they don't fine tune on this data set or anything. They don't even train on this data set. They just train on the data set that they generated, the web text data set, and then they perform on. I mean, that is a very important point, that they don't have access to these data sets in the training data. This is doing all these tasks without access to the data set. That is like one of the big key I think clues for them to try out something bigger, because this trend seems to hold. So now they showed, okay, so we saw that, okay, if you increase the model size, then pure language generation ability, predicting next word ability does seem to improve. Now what about utilizing that to solve like NLP tasks? Again, here this is different because we are not doing any kind of training. This is purely zero shot inference kind of thing, right? So the way they do translation is very straightforward. The way I showed in the French Revolution example, they just prompt it with the quote unquote definition of the task, and then they give the question, and then they expect the answer. So obviously it's not going to perform as good as the machine translation, I mean the state of the art or whatever, because there is no training going on there. But still it keeps improving, and across all the tasks. That is a surprising like discovery. For certain things it's like as good as random. So for this one, summarization, it's not performing well, but again it is improving across the parameter count. So that is the main takeaway, that different tasks, the trend of like increasing the model size allows you to have better and better performance. And this is going to get pushed significantly more to the right in GPT-3, and the performance also keeps on improving. Okay, so GPT-3. Now GPT-2, but yeah.
Time check. We have about 15 more minutes to go.
I think we'll be good.
Okay.
So the only thing is that GPT-3 I'll definitely be able to finish. I do have slides for BERT. So if we have questions or something, we can talk about it. But because it's like a deviation from GPT-1 to 3, and it involves certain things which are different. It is more, I mean, practically it is slightly more useful because smaller model than obviously GPT-3 and works slightly better than GPT-2, and also more practical. So we can talk about it, but if you have time, otherwise you can just take questions.
Sounds good.
Okay, so GPT-3, I mean, it doesn't even fit on this graph. Even if you make this log, probably it lies somewhere here. It's like 175 billion parameters. So just for scale, BERT large here, this 340 million parameters, that in my GPU, that takes about 400 megabytes of space. So when you have 175 billion, then you'll probably need like a lot of machines, and then you have to distribute the model. So break the model, the components, like let's say first 100 transformers on one machine, the second 100 on second machine, etc. So this is only like you can only do that at big companies. There is no way to have something like that on even startup scale resources. So that's like a big, in my opinion, that's a big problem. But we can see what it can do with these kinds of parameter counts. Okay, so the motivation for this paper, they say is that we saw this trend that from GPT, in GPT we had like 7,000 books data set that we trained on. For GPT-2 we had that total what do you say, I think 40 gigabytes of text. Yeah, I think 40 GB of text, which is like 8 million documents. So from 7,000 quote unquote texts or documents, they went to 8 million documents, and the parameter count went from 100 million to 1.5 billion. So in both the cases, they showed significant improvement in terms of language modeling abilities. So they are just trying to push this as much as they can in this paper. And in this process, they figure out that few shot learning works significantly well. And one of the other motivations is that as we talked about this data set creation thing, right? For each new task that someone can come up with, every time we'll have to spend time creating a data set, which is very, it takes up a lot of money, a lot of effort. Today only there was this report published, which AI startups made a lot of like basically had significantly increased valuation. 7 of them were labeling companies, some kind of like data generation companies. So it is a big problem. Like you do need a very high quality, good data set. So they are saying, okay, can we do away with this data set creation task and just allow few shot learning? And also humans do learn few shot, right? If we do know the language, then we just have to say, oh, translate in this language, and we know what to do. So they want to see whether we can push a language model to do these things or not. So I'm going to stress this point again because they do that in the paper, and it is for not for a unjustified reason, because there is a confusion between normal few shot, traditional machine learning few shot versus the definition that they use. So traditional machine learning few shot, as we talked, it involves back propagation when you provide a few examples. So there also the motivation is same, that you don't want a large data set for everything. So they have a small number of examples, but they do fine tune the model on those small examples. Even though the examples can be like 20 or 30, but they do have the examples, and they change the weights of the model, and then they perform a specific task. So for example, here prompt is cheese, and they want to translate that, right? So given these translations, I mean, we don't even know if it is a translation, but it is. So then what is the answer for cheese? So this is traditional machine learning. Here they're saying that, okay, we don't want to backprop, because obviously for such a large scale model, it's impractical. So we want to try zero shot, one shot, and few shot, and see how far we can push the ability of a language model to do that. So we want to translate English to French. So this is just the trust description. This we always require, because otherwise it can be anything. And then cheese, and then we have the prompt. Similarly, in one shot, we provide one example, and in few shot, we provide some examples of that task. By the way, there is another experiment that some people did, where they try to confuse the model, where you provide one example wrong, see what happens, those kinds of things. So I mean, those are like minor experiments that are possible, but yeah, this is the main idea, and they want to push this paradigm further.
Here
So,
is
yeah.
Sorry, just to here when we talk about task description, example, and prompt, again, this is just a simple concatenation of all of this, right? As in our input sequence.
Complete concatenation. Everything is just raw text. There is nothing going on there. And because we have this
there's no separate inputs.
Yeah. And because we have this byte pair encoding, we just write text, and then it decides, okay, where to add separator, where to add comma, I mean space, where to break a word down into two words, etc. So it's just raw text, and it'll give you the prediction.
Understood. Thanks.
So for me, the most important part of that paper, the 70-page paper, was that this scaling law that quote unquote law that they say. So they showed that when we increase the parameter count, so from 10^5 to 10^11, so this is the GPT-3 scale. When we increase the parameter count, the validation loss on our language modeling task, it keeps going down. So even here, it does not. This is not it. So if someone comes up with I don't know, data center scale language model, this might even go significantly more further. So Kritika, by the way, this is the reason probably that too. So that's like one of the lower bounds that anyone has ever achieved on language modeling. So probably that's why they were scaling everything in that in that scale.
Okay.
Probably, I'm not sure, but it could be. So here from GPT, so smaller models start leveling out. So they don't, even if you train much more, and they did a lot of sweeps. So the paper has a lot of examples, and there is another paper called Scaling Laws for Language Model, which came in January this year, which showed similar behavior. And they also analyzed the same thing for LSTM models, and they showed that transfer models scale better. So if you increase the model size, there is an opportunity to keep learning more and more. And then they also, so the longer you learn and the bigger your model is, it's going to give you better performance in terms of language modeling purely. So this is just language modeling. And then what it does with few shot and one shot and zero shot, that we'll see later. But so basically the point is that maybe in the coming few years, this might even get pushed further. It is entirely possible. Not only probably by sheer size of the model, but there have been some advances in making transformers more optimized. So there are like sparse transformers now, and it's possible that this might get pushed down further.
So is there also a curve which shows like the change in validation loss as per the increase in parameters? So what's the trade-off?
This is that, right? So
like no, like so I'm thinking of like rate of change of validation loss, not just the validation loss.
Rate of change. So in a way, this is the rate of change, because I mean, not really. I don't think they have that experience. Probably in that language modeling paper, they might, because in that paper they have exactly these kinds of experiments where they show how things improve or like get worse as things change in the parameter space, in the compute space, in the data space. So there might be something like that. But remind me, we can take a look at that.
Okay, thanks.
So the entire gist of that 70-page paper is this: GPT works well. That's it. I mean, there is no point in going through all of them. But surprising part is that for certain tasks, the largest model like touches the like state. It does touch state of the art in a lot of them, but it reaches human level performance in certain language modeling stuff. So this lambda is that language modeling, the long term language modeling. So sometimes human also don't perform too well because you have to need to remember that entire 50 word things. People don't have that kind of attention span sometimes. I don't know, so it doesn't work. Like it's not completely there. Sometimes it makes mistakes. But this zero shot and few shot, so few shot is like 85% or something, which is significant. I mean, it's really impressive that it's able to do that. For me, very important is this translation bit, because for translation, I mean, it used to be a extremely important problem in natural language processing, and there was a phase where Google shifted from this statistical machine translation to neural network based translation model. I think in 2014 or 16 or something, and they got like significant. I mean, I also remember if you try to play around with the Google Translate for a in a span of 6 months, the performance changed significantly. So probably that is something that we might be able to see using these things. So now it might potentially open up avenues for other, like scale across different languages, all those kinds of things. And there are certain things we'll talk why these languages and not others, etc. But just zero shot for these languages, I think it's very impressive. Also trivia. So this is also something I found very interesting. So the other application that I foresee for these large scale language models is using them as some kind of knowledge base. So the fact that it can say Microsoft and then Bill Gates, that means that that relationship is represented in the probability space that the model tries to learn. That in itself can be useful for certain like it can be used as a black box. So for in things like, let's say, Siri or something, right, where Siri uses, at least it used to use back in the day when it was a startup, a knowledge base, like a graph based database, where every entity has like every entity is a node and that relationship is an edge, and then it queries that database to get some kind of answer. And it's a very complicated engineering process, but it is possible that you can leverage the ability of a significant, I mean, model to augment that, or at least things that you don't know, you just if you don't have high confidence, you just push it down to the language model and then just see what it does. So for those things, I think it can be a very useful like a useful tool. So that's why I picked out like these three examples, which I think are interesting. The other quote unquote minor takeaway, the reason I say minor is because they do hide certain things under the rug, that it does not work so well for certain tasks. For example, language synthesis. So if you look at the examples that people posted, so there are two groups of people for GPT. It's either you hate it or you love it. And the people who hate it have given a lot of examples where it certain statements, because if you're only prompting the highest probability thing, then sometimes it does go into this loop where it starts generating the same statement again and again and again, which is a problem with all these language models, where sometimes it happens. That's why we use those temperature and all those things while to sample. So that is a problem. There are certain times where when you try to generate long text dumps, it will start contradicting itself because, I mean, there is no explicit mechanism to prevent it. So that also happens sometimes. The other very discouraging thing for me is that for very simple common sense stuff, it does not work well. So for example, if I put cheese into fridge, will it melt? And the answer to this, it does not seem to understand. So if you create these kinds of tasks and ask the model to predict something which are basic physics stuff, like realities of physical world, which everyone knows, the model does not do well for whatever reason. I don't know why that's the case. I don't think they have put in a lot of effort to figure out why that. I mean, there is the right way to figure this out, but I don't think there is also speculation for this. The other thing that they claim that it works well at, but I can bet like a good amount of money that this is probably some kind of memorization. So they show that for 2-digit addition, subtraction, up to 5-digit addition, it works. It seems to work. By the way, if you look at the trend, it keeps going down significantly, the accuracy. So for 2-digit addition, for few shot, it works perfectly well. For 2-digit subtraction, almost there. And then when you go to 5 digits, it doesn't work well. So it's not learning the rules of arithmetic in any way. I mean, if it is, then why would it give 25% accuracy on 4 digit and 9% on 5 digit? There is no way. So 90%, it is some kind of memorization. It's happening inside the model weights. Uh, that is an open question, basically. And also for multiplication, even for 2-digit, it's very bad. So one of the reasons I saw some discussion on the web, and they're claiming that, I mean, if you look at some of the Google books where there are tables, like statistics books or something, where there are tables and tables printed out, where you have like a column of something, then a column of something, and the third column is the addition. So there are examples of such things that it somehow memorized these things. So that is most likely that is what's happening. Yeah, so I think those are like not so impressive cases for GPT. Now I'm going to end with like just 2 slides, so like 2 minutes. So one thing is like these are basic limitations, and I think everyone, even the GPT paper, the people who are very bullish on that also agree that this is a prohibitively large language model. Like 175 billion is ridiculous. Yeah, I mean, no hiding from that. The other is that there is, I mean, I personally feel that constructive application of these things are at least right now limited, because you cannot use it in any setting where it might compromise, let's say, reputation of a company, or even, I mean, anything like that. You don't know where it's going to fail. For example, if you prompt it with some Buddhist religion, then it prints out like good text, and then if you do Islam, then it prints out all violence and everything there. I mean, it's you could have probably imagined that, because the kind of data that it's trained on, but there is no way to prevent such a thing unless you have you enumerated all the cases. And if you can do that, then why not just use that technology as your language model, and why use this, right? So the error modes are unknown, so that prevents a lot of applications. Another biggest thing that I am very I think a lot about is low resource languages. So for us, let's say, I think India has close to 700 languages and dialects. The world has like 7,000. But this ability so far is only in English, to some extent in French, Russian, etc. A little bit in German. But after that, this goes down. The model relies on huge dumps of generated text, and that only happens in English these days. So this is a big problem, and that, I mean, people would say there are some debates in the internet saying that, oh, is language a solved issue? It's definitely not, right? For what do you do for low resource language? It's a big issue. Then data bias is clearly an issue with all these machine, like black box models, where you don't know. For example, it always predicts doctor and a nurse as female. Just one example, but this happens all over the place, and there is no way to say why. So because so for things like BERT, you can visualize the BERT, or even GPT, you can visualize the attention mask, and then you can say, oh, this is why this happened. Or so you can have allows some kind of interpretability. But when you push transformers to the limit of, I mean, all the compute that you can afford, then this goes away. So that's a big problem. Another, like, ending on an even sobering thought. So there is this challenge called the Alexa challenge, where Amazon has this competition where the universities participate. They are provided all the resources, and then they launch the users or the testers of this bot that they create are of Alexa, and you can say, Alexa, let's chat. Once you say that, it goes into this mode, and then you can have a conversation, and the user can rate the chatbot on like emotional connection, facts, coherence, all those things. So for this is the second place prize this year, second place winner this year, like runner up. This is the Stanford model that they designed. Something. So for this entire thing, language model is used. It requires all this entire like peripheral systems around it, and those are those are not trivial on their own, right? So language model is just like a part of the solution for all these kinds of software or problems, and it's not like AI or AGI or whatever people claim it is. So here, by the way, they were using GPT-2, so it's not something like toy. They were using the bigger GPT-2 model. So then still by the way, they did not win. So it tells you that it's not everything. So I think, yeah, so this is the saga. If you want, we can talk, you can ask questions about BERT, or we can go over it, but this is it for the GPT stuff.
Great, thank you. We are over time, but
Sure.
I'll pause for some questions.
Sure, yeah.
In case there are no questions, can we revisit that slide about where you were talking about engineering hacks that turn different tasks into language modeling tasks, and
Yes.
Maybe just like talk a little more about how that happens, because in the example of how transformers work, we looked at sequence to sequence, right? But if you want to do sequence,
no, we did not look at sequence to sequence. We looked at transformers transform sequence like vectors to vectors, and then you can do whatever you want with those vectors, right? So in this case, the way sequence nature is enforced is by masking of the attention masks, basically. So for example, let's take an example of similarity. So for sentence similarity, we have a text dump, we have another text dump. Then you create this input where you have a start token. This is a separate token, by the way. And so embedding of size D, whatever is the dimension of the model. Then sequence of other tokens, so x1, x2, x3, blah, blah, blah. Then another token, which is the delimiter to allow the distinguish between two subsequent sentences. Then another sentence, and then the end token. Now this is passed to the transformer. The output of this is like an embedding of the same size as this one, right? Now we can concatenate those together and then add a fully connected layer where the size is this cross the number of tokens in your vocabulary, or the number of tokens in your in the task. So in this case, let's say similarity only gives us yes or no, like is it similar or is it not similar, or it can give us like a degree from 1 to 10 or something, which whatever be the amount, the classification, whatever. It can also be a number, by the way. So it can be a number, and then the loss can be regression loss, right? It could be anything. So the point is that whatever you get here is going to be of this dimension. So then there is a fully connected layer dimension cross your output dimension. That's how the like model is augmented to solve this problem. Does that make sense?
Yeah, so that's how it would work for anything, like even classification or
everything. Yes, yeah.
Okay.
So that's what so for example, if you come up with a task like summarize, like generate abstractive, like doing abstractive summarization or something, then that doesn't fit into this model. It's like it does not, it is not addressed in this series. Entire series is not addressed. So what you can probably do is that get the entire document and say summarize this, and it might generate some abstract, but then creating a loss function for that is, it's very difficult. That's why those tasks are very difficult, and those are not addressed in these papers.
Okay.
What about the like sort of articles and all that were generated by GPT-3 in their demos. Like people have generated 200 word, 500 word articles, and in fact, they used to add a twist at the end where they say that this entire thing was generated by GPT-3. So how's that happening?
That is purely language modeling. So given the prompt, you just start sampling the language model, and whatever it produces is the output.
Got it. And you just keep going for how many ever words you want.
Yeah. So, and then that also involves certain tweaking. So they claim that if they claim that it must be true that the paper did not have nitpicked examples, but a lot of what we see in the web is nitpicked. So people generate multiple answers, and they see whichever makes more sense. They just use that. But all of them work the same way. They keep generating text based on. But by the way, important thing is that let's say we generate x1 to x, we have xn plus 1, then input becomes the entire thing. So however much we can fit into the window into the input context, all of that goes, and then you predict the next word, by the way. So it's like you put that back into the input and then you generate. So that's how it works.
But I have one quick thing. So in the UI, the few screenshots I've seen of the UI, you can specify the number of words or characters you want the output to be, right? And so does the output then change? As in, does it somehow also capture that because it's 500 words and not 1000 words, therefore I should conclude in a certain way, right? Does that change the model sampling?
So there is no right answer to that. We don't know whether model understands that and changes the output based on that or not. But the answer is definitely different.
Right.
But we don't know why that is the case. Yeah.
As in, I'm just so like what I'm thinking is like, let's say you specify 500, right? Therefore, then does it like change is 500 an input to the context, right? So therefore, it changes the kind of, I don't know.
So let me give you one example. Let me give you one example. For example, let's say actually let's try to go to the one of the I don't know. Let's see. Okay, I think it's. Yeah, so we have a demo here. By the way, this is a much smaller model, and I don't think they are maintaining this properly. But let's say so Gates came, right? It's with 94% probability. Now, let's say I do this thing. Okay, so it does. Oh, I should do this. By the way, that is something also weird. And now it's not giving me anything. So this is the context. But if I give a context where it's like a dump of text related to Microsoft, then there is a high chance that Bill will be the next predicted word. So if the context is significantly larger, then it does change the probabilities of the text that is going to follow after that. So if that was the question, that if you have a bigger context and does that change what it generates, then yes, that is the answer. And usually that is why few shot works better than zero shot or something.
No, my question was, and we can continue on this. Is 500 the number of characters in and of itself also input on context, right? So like the number of characters for the output, is that also somehow
it's not. No, it's not. Okay. So that is just how many times do you want to sample the model, and then that is the. It's basically the engineering thing. So the API that calls the model. But that's a good idea. Probably there may be some tasks where you do that. I'm sure they don't have anything in these, but for BERT there are certain things that they have where you specify span of certain answer or something. So there are similar things going on in different experiments, but for this one they don't have such a thing.
Got it.
So you just say how much, like you specify a context, and it will try to get like whatever it generates, the biggest thing that it can fit into the context, that is going to be used. But apart from that, whatever it samples is.
Got it. Denny said he had a question.
So, I totally see the appeal of, something like a language model or GPT, because, being able to understand human language or being able to generate it is probably like the highest ideal in, this field. But I'm just curious, like, are there like, building blocks of something like GPT-3, which you think are, more practical for a lot of other purposes and like, solve real problems in a more, interesting way?
So from GPT 2 and 3, they are more uh, for curiosity, like research stuff usually, right? But GPT gave us this and transformer. So the ability that just using this transformer gives us the ability to do this fine tuning. That is something people can use practically. But this idea then was pushed to like even more to a much better level to by BERT. So let me just show you one slide where the idea is that you don't have, so this is the difference in GPT. You're only seeing it, you're only doing the language modeling, and there is a lot of things that you miss out on. But for most of the tasks we can see the entire thing. So let's say it's question answering, you can see the entire question. I don't need you to look at one, then second or third, or like mask while you are generating the output for the first one, right? So they are using full power of the transformer, and they have different kind of transformations in problems, but this is significantly more practically useful. I mean, useful as in better. I mean, it's easier to deploy, easier to fine tune, easier to train, etc. And also less parameters than GPT-2 and works better in a lot of tasks. So, but the idea of using all these transformers, that is a contribution of GPT. So it is a building block that people use to to whatever, however many transformer layers they can, and it works very well.
Are you saying that GPT uses the mask even in, for example, the encoder section?
So the thing is that there is
Or
no
is it?
encoder decoder in
Oh, I
GPT.
see.
It's
Okay.
it's just so if you look at the paper, they say that we are using the decoder layer of the encoder decoder architecture. I
Oh,
did
okay.
not bring it up because it's like a technical baggage, this encoder decoder part, because in the way transformers is used in GPT is just that you have a sequence of into certain sequence of tokens where you want to take into consideration some interdependent nature of the input. That's it. But this decoding or encoding, because there is you're not encoding a given sequence to anything, right? It's just, so I mean, yeah, so that is the difference between, that is also a difference between GPT and GPT-2, by the way. So GPT and BERT. BERT says that we are using the encoder part of the attention is all you need paper, and these people say we are using the decoder part. But in terms of the computation that goes on, there is no difference. It's just that this is using the masking part and this is not, and it's therefore this is allowing more context and doing better on certain tasks. But then the problem is that you can't use this as a traditional language model, because you're not preventing it from seeing the next thing. So that's a problem. But usually you don't always want a language model. You want something that works for you. As that is exactly what Danny was saying, that all this is working very nicely, but so what? So the thing is that, okay, so now you take the components of that and make something which is 400 megabytes. Is not significant. It's not too bad for certain applications. Like, it's very nice. And then there is a series of research on BERT like Roberta and DistilBERT, etc., which are significantly smaller, and it works very well. But you cannot do language modeling as far as I know on all of these. So language modeling like this, like give me the next word, give me the next word, give me the next word. You can't do that.
Got it. Got it. Just by the way, on a side note, you mentioned that you had tried with GPT-2, right? Or BERT, and that was around
But
400 MB.
yeah.
I think GPT-3 is 350 gigabytes of memory.
So for the reference, my new machine has 11 gigabytes of memory. So I mean, you require a lot of them, and then this is just for keeping. But the problem with these is that, so just one aside, in the GPT paper, is this? Yeah, this is the GPT paper. So they have a place where they show the batch size, and they show that what is the batch size that they are using, and that is also ridiculous. Yeah.
Wait, when you say memory, we're like talking about runtime memory. So when you say it's a 350 GB model, it has to be loaded into your RAM. Like that's.
Yeah. This is RAM.
Oh shoot.
Yeah.
I kept thinking it's like your disk space. I didn't realize it was RAM. Oh shoot.
Oh, by the way, so like these are the sizes of tokens that they have. So it's trained on 110 billion tokens. Wikipedia is like 3 billion tokens. This is the size of, so this is the data that you train on. So you first load that whatever 350 gigs into memory. Then you have this data set to pass through that 350 gigs multiple times to make it work. So, I mean, training is a completely insane. So yeah, look at the batch size. Number of tokens, they have 3.2 million tokens. I mean, how?
For reference, I think the normal batch sizes are like 64 and 2048 and all, right?
So the thing that I'm training on right now in computer vision, I have a batch of 6 because I can't fit more things into my GPU.
Yeah. Wow.
So loading the model is just part of the problem. After that, you need to pass a large enough batch size. So there is something to learn, because if there is just one like batch size is very small, then it's highly stochastic. So then you don't generalize well enough. So people try to maintain like a good ratio between learning rate and batch size, etc. So if you see, the ratio is maintained here in the batch size and learning rate every time. But in order to be able to fit this batch size, I mean, it's ridiculous. How does one train this thing? So I don't know exactly what are the technical details of their training architecture, but then that in itself can be a very interesting read, because trying to train this, there is something called data parallelism and model parallelism, and both of them have to be used in order to train such large model, and the way they implement that would also be very interesting to see. But yeah, I mean, the scale is just ridiculous. That's the bottom line.